All right, so on Monday we spent some time starting chapter 12, which is on alcohols. And so, just to remind you what the functional group for alcohols looks like, it's an sp3 hybridized carbon that holds an OH. And so if that sp3 hybridized carbon holding the OH has only one carbon group attached to it and the rest hydrogens, that we call a primary alcohol. We can also have examples where we have two carbon groups attached and only one hydrogen. That would be a secondary alcohol. And then the other example that we could think of is to have that carbon that holds the OH have three independent alkyl groups. So that would be a tertiary alcohol. So what this chapter deals with is a few reactions of how to synthesize alcohols, which is what we'll cover in this video, and then on Wednesday we'll talk about reactions that you can do with alcohol. So we're going to go through a series of reactions, some of which are review in terms of how to synthesize alcohols, and that's what the subject of today's video is. So the ones that you should remember from Organic 1 is synthesizing alcohols from alkenes. We really have two ways that are synthetically useful. You learned three ways, but there are really only two that actually provide a reasonable outcome for these types of reactions. And so if you don't remember these, you should go back and review them. So the first one is called the oxymercuration. And that oxymercuration gives me the Markovnikov products. So that's going to be the case where we'll add the water across the carbon-carbon double bond in a way such that the hydrogen goes on the less substituted carbon and the OH goes on the most. So here's what the reagents look like. We do this with mercury acetate, so a mercury 2 salt in the presence of water. So water serves as the nucleophile. And then at the end of the day, we end up reducing that first product with sodium borohydride. So that's what the reagents look like for the oxymercuration. And at the end of the day, what we end up with is hydrogen on the less substituted carbon, OH on the most. So this is one route that you guys have learned to synthesize alcohols from Organic 1. And just as a reminder, what ends up happening here when you have this mercury with the two acetate ligands, that carbon-carbon double bond will attack the mercury and spit out one of the acetates. And then we get this key intermediate where the mercury is shared between the two carbons of the double bond. But now that mercury has three bonds, it becomes positive. So you might recall this is the mercurinium ion. But then what happens in this case is when the mercurinium ion forms, water will be attracted to the more substituted carbon of that group because that carbon can better withstand the buildup of a positive charge. And so we'll dump the electrons from that carbon-mercury bond onto mercury. And so what we get as the initial intermediate is addition of water at the more substituted carbon, and then that mercury ends up on the less substituted carbon. And so the next thing that happens is we'll neutralize that oxygen by having one of the protons fall off. And so then we get to this species, which looks a lot like the alcohol product. That's where we get stuck after step 1. And then all step 2 is therefore is to reduce off that mercury. And so sodium borohydride will do that, replace that mercury with a hydrogen. That's how we get to the final product. But the key thing to recognize, this is going to be the way in which we can add water across the double bond such that we get the Markovnikov addition where hydrogen goes to the less substituted carbon and OH goes to the most. The other way we can make these things from alkenes that is synthetically useful is the hydroboration reaction. And And so this is the route that gives us what we would call an anti-Markovnikov product. We say that because at the end of the day, the hydrogen ends up going on the more substituted carbon, and the OH ends up going on the less substituted carbon. And so the way we do this reaction, we treat the double bond with borane, and then we work this reaction up in a second step with sodium hydroxide, hydrogen peroxide, and water. And so that series of events leads to an alcohol product, but it's a bit different than the first example because we switched the order in which the oxygen and the hydrogen add. So in this case, the hydrogen adds to the more substituted carbon and the OH adds to the least. Briefly, in terms of why that happens, what happens in this case is that one of these boron-hydrogen bonds will approach the carbon-carbon double bond, and we have what we call a concerted process where all these bonds form and break at the same time. So the double bond will use its pi electrons to add into the empty p orbital on boron, and then this H with its electrons will dump onto the more substituted carbon. And so what we end up with there is hydroboration of the alkene in the way where the hydrogen goes to the more substituted carbon and the boron to the less. And then really all that happens at this point is that we will do that oxidation step in the second step. And all that does is replace that boron with an OH. In class on Wednesday, I actually went through that mechanism. If you were interested, I would suggest getting some notes from some folks who made it to class on Wednesday, but that's not something I would test you about. Really, all I want you to recognize is that the only tools in your toolbox right now from sophomore organic for synthesizing alcohols comes from these two reactions of alkenes. That's the major take-home point. All right, so if we go back, that's sort of one route we have to synthesize them from alkenes. The second route that we have that is not such a good one, but we can actually make alkenes by substitution. And so that's sort of in line with what we have been talking about earlier in this semester. If I have a reasonable alkyl halide like this alkyl bromide that's capable of SN2 chemistry, I can actually treat that with something like sodium hydroxide. And hydroxide is a reasonable enough nucleophile to do an SN2 substitution such that I would make some of this alcohol product from substitution. The problem with this approach is that the nucleophile we've chosen to use, sodium hydroxide, is quite basic, and so anytime we think about substitutions, they go hand in hand with their elimination counterparts, and particularly when we use a very strong base like hydroxide, we would get substantial amounts of E2 elimination products. And there's really no way to prevent that. And so this would not be a very high yielding approach to synthesizing alcohols. So all this to say that there are a few ways that we know from sophomore organic, one, that will allow us to synthesize alcohols, but we've got the next subset of reactions are probably by far and away the most common way you will see people synthesizing alcohols. And so these are reactions that are called reductions. And we're going to talk about two subclasses. So they're hydride reductions. And what that will do is that will reduce a carbonyl, a C double bond O, to an alcohol by delivering an H minus. And then we'll see some carbon-based reductions where we do the same thing, where we're delivering a carbon nucleophile instead of a hydride nucleophile. So we have two ways in which we can reduce things with hydride. The most common one for aldehydes and ketones would be to use a reagent called sodium borohydride. and it has this Lewis structure NaBH4. And so here's what that reaction will look like. I'll take a ketone like this one, something with a carbonyl, and I'll treat it with this sodium borohydride reagent. And we do that typically in a mixture of water and ethanol, so protic solvent. And we'll see why we need that protic solvent in just a minute. The result of this reaction is a pretty simple one. We'll convert that C double bond O into an alcohol by delivering a hydrogen and some electrons to reduce that carbonyl. So the reason this happens is that carbonyl is pretty polarized. That carbon of the carbonyl is partially positive, and that oxygen is partially negative based on the electronegativity difference. And so what will end up happening if we think about the structure of sodium borohydride, it's going to be this boron atom with 4 hydrogens crowded around that nucleus, and so that boron is negatively charged and it has this sodium plus counterion. And what ends up happening is, since that boron's negatively charged, it can actually spit out an H minus from one of those hydrogen bonds that are attached to it, so that one of these hydrogens can take its electrons and deliver them to that partially positive carbonyl carbon, and then the electrons will push up onto the oxygen. And so if you can follow what's happening there, what we'll get is delivery of that hydrogen and formation of an alkoxide nucleophile, and that's where the water or ethanol in the solution comes into play. We'll use that as a proton source from the solvent. That O- will pluck off a hydrogen from water, and that's where we get the alcohol product. And so what you can see in this case, if I use a ketone starting material where the carbonyl has 2 carbon groups attached to it, this is a good strategy to make secondary alcohols. And so we can do the same thing with aldehydes, and that will give us access to primary alcohols. So if we look at this one, we'll just do a few examples here to drive this point home. So we'll work through quickly three examples, but I think it's pretty straightforward in terms of what's happening here. All right, so these would be 3 reasonable questions for an exam or something like that. So, and all that's happening here is, again, that sodium borohydride serving as an H- nucleophile. That's going to attack the carbonyl. We'll go from a double bond to oxygen to a single bond to oxygen of that carbon. That's why we call it a reduction in oxidation state. And so in this case, I would end up making this primary alcohol because I've reduced an aldehyde. In the bottom 2 cases, I'm reducing a ketone, so I'm going to get a secondary alcohol. But again, same idea. I'm delivering that hydrogen to the carbonyl. It's giving the electrons to the carbonyl oxygen. I go from the carbonyl and the ketone to a secondary alcohol. Same deal with this last one. Okay, so easy peasy. So that's probably, sodium borohydride is probably the most commonly used reagent for reducing ketones and aldehydes. There is another reagent that you will find in your book that can do this as well. That reagent is called lithium aluminum hydride. It has this structure, lithium aluminum with 4 hydrogens. So it kind of looks like the sodium borohydride. If you look at the periodic table, aluminum sits right below boron, so they react in exactly the same way. The difference here is that the lithium aluminum hydride is significantly more reactive. And part of that is that we have to be a little bit more careful with this thing because it turns out to be pyrophoric. So if this material gets wet, if it soaks up water from the atmosphere, it can ignite. And so you can actually have pretty serious fires with this stuff. But the flip side of that is that you have to have aprotic solvents. So this reaction works just as fine, just as well. So I can actually reduce ketones with lithium aluminum hydride, but the way that we would write the reaction looks a tad different. We would actually add the lithium aluminum hydride in an aprotic solvent like THF. So THF is a cyclic ether. That material doesn't have any acidic protons, so we don't have to worry about the lithium aluminum hydride catching fire. So we would run that reaction in the first step. That will deliver the H minus to the carbonyl, but then in the second step we would add a little bit of acid and water to put the proton back on that oxygen. So we just do this in 2 steps instead of 1, but the outcome is exactly the same. Now, you would not see many synthetic chemists going to the lab and using lithium aluminum hydride to reduce a ketone or aldehyde, because it's a much too powerful reagent to do that than sodium borohydride, so there's really no reason to use it. The analogy I used in class is it's kind of like using a shotgun to kill a fly. But we will see other reactions of lithium aluminum hydride where that extra reactivity is the only way we can get reactions to happen. But you can use either of these two interchangeably. So there are lots of questions like this in your problem set to take a look at. Okay, so those are reductions by delivering an hydride, H minus. The second step that we're going to use, I got to figure out I was using A and B. So the second type of reductions that we can see are with carbon nucleophiles. So we're going to introduce briefly a new type of compound. These are called organometallics. So we're going to see a series of organometallic carbon nucleophiles. The most common one for the approach we're going to talk about today are these things called Grignard reagents. So what a Grignard reagent looks like is this. We can actually take material like ethyl bromide, so an alkyl halide. If we think about that alkyl halide, that carbon is polarized in this way, where the carbon is partially positive and that bromine is partially negative. And the reason, one thing we can do because of that is we can actually use that carbon in things like substitutions as an electrophile, right? Because that carbon's polarized to be partially positive. We can turn that material, though, into a Grignard reagent by treating it with magnesium 0. So we can treat it with elemental magnesium, just magnesium metal. What will end up happening in that case is the magnesium will insert in the carbon-bromine bond, and we'll get what's called a Grignard reagent. So we'll have this material where now we have a magnesium attached to the carbon. And what ends up happening there is we actually have moved all the way to the other side of the periodic table, from bromine on one side all the way over to magnesium on the opposite side, and that changes the polarity of that carbon bond. And so now that carbon is actually partially negative and that magnesium is partially positive. And so really what this gives us now is this gives us a carbon-based nucleophile at that carbon. And these Grignard reagents really behave as though we have synthesized a very strongly nucleophilic species, an alkyl anion. So they actually behave as though that ethyl group is an ethyl negative. And so if you can make something like that, it should make sense that it should be able to react with a carbonyl and add to that carbonyl and reduce the number of bonds to the carbonyl to make an alcohol. So this is exactly analogous to the reduction with hydride nucleophiles. Here we're just using a carbon. And so we can use these Grignard reagents to reduce carbonyl. So if we look at, for instance, a simple reaction like cyclohexanone, and let's say, for instance, I react this with methyl magnesium bromide. And then I'd follow that up with a little acid and water. So same idea, these Grignard reagents, much like lithium aluminum hydride, are pretty basic, and so we have to keep them away from protic solvents. But really all that is happening here is that this Grignard reagent is behaving as though I have a methyl minus, and it will add to that carbonyl and dump the electrons onto the onto the oxygen. And so what I've done is formed a new carbon-carbon bond at that site and generated an O minus. I get stuck there until in step 2 I add in my acid source that's only there just to put that hydrogen back on the oxygen. So this is another way in which I can reduce carbonyls. So I would get this material here. So anytime we use this carbon-based nucleophile addition to a carbonyl of a ketone, this is the only way we have to synthesize tertiary alcohols. All right, let's see a few more examples of this to kind of drive this point home. You can do this with aldehydes as well. So let's try this one with, say, phenyl magnesium bromide. All right, let's do this one with something different. And then we'll do a third example down here. I don't know, let's use ethyl magnesium chloride. So you can do this with carbon chlorine or carbon bromine bonds to make Grignard reagents. But once again, this should be pretty straightforward. Really, all we're doing is adding this carbon group into the carbonyl of whatever species we're alkylating. And so in this particular case, I would deliver this benzene ring directly to the aldehyde carbonyl. So if I alkylate an aldehyde, I should make this secondary alcohol. Now I have vinyl magnesium bromide with a ketone. So I would expect to add that carbon-carbon double bond directly to the carbon that used to be the carbonyl, make an alcohol there. So I get this tertiary alcohol. And then in the final example, I can do the same thing with ethyl magnesium bromide. I can deliver that ethyl group and make this alcohol. So another synthesis of a tertiary alcohol. So that's the addition of carbon-based nucleophiles to carbonyls to synthesize alcohols. There's a second type of carbon-based nucleophile that I want to introduce really quickly. This also works with what are called alkyl lithium reagents. It's not a whole lot different here. You take, again, a halide like this butyl bromide. If I take and throw in elemental lithium metal, lithium 0, I will replace that bromine with a lithium. You know, lithium is at the very end of the periodic table, so it only takes one bond, so we don't have that bromine hanging around anymore. But the same thing has happened. I've polarized this bond where the carbon is negative and the lithium is positive, and so this system really just behaves as though I have a 4-carbon nucleophile. And so if I take that guy and I throw it in with a compound that has a carbonyl, so we can take one of these ketones like indanone. If I throw in butyl lithium and then follow that up with acid and water, I can use that butyl lithium to alkylate that ketone. And I would get this alcohol. So you will find an awful lot of practice in your problem set about doing these types of alkylations and reductions, which are probably the most important way that we can synthesize new alcohols. We do them directly from ketones and aldehydes. This is all we covered in class on Monday, and so on Wednesday we'll pick up with talking about reactions of alcohols. Now that we've learned a lot of ways to make alcohols, what are some of the things we can do with them? And so that's what we'll pick up with on Wednesday.